Hello students, I hope all of you are doing well, particularly in this COVID-19 pandemic situation. I wish that all of you are in best of your health and spirits. So continuing with our coursework that was on quantum mechanics and statistical thermodynamics, I'm going to introduce statistical thermodynamics today. So as you know, we have studied quantum mechanics. From your earlier classes, you also know classical mechanics. You also know that this quantum mechanics deals with the microscopic properties of matter, and classical mechanics describes the bulk properties or macroscopic properties of the matter. That is, if you are talking about pressure of a gas, boiling point of a liquid, melting point of solid, these are all comes within the realm of this classical mechanics, right? And in quantum mechanics, we study how the electrons moves around a nucleus, how the vibration in a molecule takes place, how a molecule vibrates. So we talk about, so if we want to understand the molecular motion, motion of an electron, motion of an atom, of an individual atoms, then we take the help of quantum mechanics. So we have already studied the models of quantum mechanics that deal with rotational motion of the part of a molecule, with a vibrational motion of a molecule, and the electrons model of an electron. So these are all things that we studied in the which we say that these are the microscopic properties of a matter. So but somehow, if you correlate these individual motions of the atom or molecules can be correlated to the bulk properties. For example, pressure of a gas is a bulk property, but at a molecular level, we know that the molecules keep striking at the surface of the wall and of the container, and so each of them, there are thousands and hundreds and millions of molecules in a container which might be moving, and each one of them strikes the surface of the wall of the container, and that gives rise to they exert a force, and the summation of that force gives us the total pressure that we calculate as a bulk property. So the individual to describe that individual motion of one molecule within the container, we need this quantum mechanics. So and if we sum it over, if we take a statistical view of the entire large number of such molecules moving in a container, then we can get to the classical picture of pressure that we usually know. So here, so starting with quantum mechanics, starting from the individual motion of the molecules, is it possible to reach this kind of situation where we are able to connect this entire evolution of the property, starting from an individual atom, molecule, and then the whole matter, a solid or a gaseous system, as we described in a container with large number of atoms and molecules. So this is possible with the help of what we now know as statistical mechanics. This is acts as a bridge from individual properties of an atom, of a molecule, to bulk property, that a large number of molecules bound together, or may not be bound together. They are bound together in case of solids, not bound together in case of a gas that we typically describe in while describing pressure and other properties. So statistical mechanics used to connect the individual properties to the bulk properties of the matter, and so we say that it acts as a bridge between quantum mechanics and classical mechanics. So that is, it deals with the average behavior of the large number of molecules, and when you average it together over a large number of molecules, you get the classical picture. So there are certain analogies between quantum mechanics and statistical mechanics that we need to understand at the very outset. So this analogy that I am going to talk about is based on the mathematical point of view, that is in a mathematical sense, there are certain analogies that we should understand, and it will help, we should know, and it will help us in a better understanding of the concepts. So first thing is that in quantum mechanics we know that wave function was the basic thing that described all the information, that contains all the information about the motion of the molecule or atom. Similarly, in case of statistical mechanics, we are going to define something called partition function, which contains all the thermodynamic informations about about a bulk sample of a matter. So we also note that in the observables, the properties we describe in quantum mechanics are related to the expectation values and which are derived and calculated from wave functions. Similarly, here we will be describing observables and properties in case of statistical mechanics which are related to the average values and calculated from partition functions. So let us consider a system which has n number of molecules and the total energy is constant as denoted by E. But we have to consider this fact also that it is not possible to definite about how this energy is shared between the molecules, although the overall energy will be constant. And the molecules, because the molecules are going to be randomly moving within a system, if we are considering a gaseous system. So collisions between the molecules will result in redistribution of energy, and it will also change their quantum states. There will be exchange of the quantum states as well within the molecules. So we call this distribution of energy is reported in terms of population of a state. We call it population of a state. That is, we say that ni number of molecules occupy an energy of EI, or we can say that ni number of molecules have energy EI, epsilon I, as denoted here. So the population of the states remain almost constant during this motion and all those things that happen. But the precise identity of molecules in each state may change at every collision. So within a given energy level, there will be same number of molecules, in other words, but the molecule which might be initially in energy level 1 may move to energy level 2, and vice versa, and the one which is in energy level 2 might come back to the energy level 1. So this might happen during the collisions that happens. So that's what we mean here, that the population will remain constant, but the precise identity of the molecule may change. So this is the population of state that we are going to calculate here. In this we need to know how the energy is distributed between the molecules. If we consider a gaseous system which have large number of molecules, if it is so we also assume that the molecules are moving independent of each other within the system. We are at this moment we are not going to consider any interactions. So that is, we are going to take the simplest view, simplest case, where there is no interaction between the molecules, and so there is no contribution as such from these factors, as we really in a real system will happen. We also will employ a principle of equal a priori probabilities, which means that all possible ways of distribution of energy are equally probable. Okay, and we also learn we are going to learn here in the coming discussion that most probable population will be for any given energy level will depend on a single parameter that is called temperature. So it is a temperature dependent distribution. Temperature is the key parameter that will determine the distribution of energy, distribution of molecules within the different energy levels. So and it will through this discussion we will also be able to justify molecular, we will be able to provide a molecular justification for the concept of temperature. And let us assume that we have different energy states, epsilon 0, epsilon 1 and so on. We will we also would like to make it clear, I would like to make it clear here that we shall always take the lowest available state. The lowest energy state will be taken as 0, that is epsilon naught will be equal to 0. In cases where the epsilon naught is not 0, some adjustment will be required, such as in case of vibrational motion. If we are considering vibrational motion, then we know that if there is a 0 point energy, E naught, epsilon naught is not equal to 0. So in those cases we will be adding, there will be some adjustment will be made later on, but initially when we work out the calculations for the population, we will be starting with assuming that it is 0. Lowest available state is 0. So that is how we go forward. So that's what I said, that we have to add a constant to the energy if there is something that if the lowest energy state is not equal to 0. So suppose we have n naught molecules. So that's we are going to discuss this instantaneous configurations. So a given configuration can have a different instantaneous configuration. We will just discuss this point. At any instant there will be n naught molecules with energy epsilon naught, n1 molecules with energy epsilon 1, and so on, such that the overall, this you sum it over n naught plus n1 plus up to nn, which should be equal to the total number of molecules, capital N, as shown over here. The specification of the set of population is a statement of the instantaneous configuration of the system. So for any given energy, for a given system, we can visualize a large number of molecules and having different instantaneous configurations, and within this instantaneous configuration the population may keep the population will keep fluctuating. So suppose we have n number of molecules, and the configuration there could be one configuration that we can think of is that all the molecules are in the initial epsilon naught energy level. That is, all the molecules have same energy. So we can write that configuration as N000. So this is the E1, corresponding to E1 there is 0 population, corresponding to E2 there is 0 population, and so on. And corresponding to E0, epsilon naught there is N, and all the molecules in the system are having same energy. In that case we write this way. Similarly, if molecules, suppose out of these n number of molecules, 2 of them move to the first energy level, so the population here will be 2, and then we can write here as n minus 2, and so the first excited state will have energy as has the population as 2, denoted by 2. That is, 2 molecules are in this energy level, whereas all others are in the lowest energy state. So this is the way we will write a configuration. So the latter configuration, this last one that we showed, the n minus 2, 2, comma 0, so on. This configuration is more likely to be found than the former. That is, when the one that we are considering with equal energy to all molecules, that is least likely and can be achieved in only one way. because it will be achieved in only one way, its probability is very, very less. But if you consider this second configuration, it can be achieved in half into n minus 1 different ways. So this can be shown in the next slide. Sorry, it is. So we are going to show this how we are going to. So all these things will be picturized. So in this, the first thing that here, the point that I would like to mention here, that we are here again while making out such distributions, we are ignoring one thing here, that is the keeping the total energy same, because in these two distributions the total energy of the system will also change. Okay, but we are ignoring that fact. We are just focusing on how we are going to achieve different types of distributions, and then we will later on will come back to it and impose that restriction, that is that energy has to be kept constant. So that part we will be coming to that constraint will be applied later in this section. So as a result of so what we are saying, we are going to discuss here, that is initially even if we start with this configuration, it will likely to change to such configuration because of the collisions taking place between the gaseous molecules. So there is more likely of it to be found, the population to be having this kind of greater population distribution in this manner. So system is free to switch between the two configuration. That is the other way of saying it, the same thing, and would show properties characteristic almost exclusive of the second configuration. A general configuration of such N0, N1 can be achieved in W different ways. That is, we are defining the different ways in which we can achieve a configuration as W, denoted by W, and this will be called the weight of the configuration or statistical weight. But while discussing, we can in this context we will be using simply the word as weight. The weight of the configuration is given by the expression this n factorial by n0, n1, n2. So this for if we have different energy levels, considering all of them, we can have this kind of expression. And here x factorial is given by x into x minus 1 into 1. That is the factorial which you know from your classes in mathematics. And 0 factorial have been defined by as equal to 1. And so if you apply this principle, then in that above case, when you have n number of molecules, you will arrive that W is given by half into n minus 1. So so just consider this picture. This is what if you are considering 5 0 0. If we have 5 number of molecules, 1, 2, 3, 4, 5 different colors, they are all distinguishable, but of the same type of molecule, but we are distinguishing between with the colors, help of colors, and these are different energy levels. So 1, 2, E0, epsilon naught, and epsilon 1. These are two energy levels. So the first picture is that all the particles having same energies. The first one. And the second is that there could be we write the configuration, second configuration, that two of them are in the next are promoted to the higher energy level state. So how many different ways we can do that? These are exactly 10 number of ways of doing that. So actually so you can promote either these two to the top level, second level, or any two energy levels, so any two particles to the level. So you can do it in different ways, and the total number of ways you can do it is 10, which can 10 different ways in which you can achieve different configuration which are distinct from each other. So these are this is to show the different 3 2 0 configuration have to be written in this manner. So this shows that population of the ground state is 3, population of the next first excited state is 2, and this configuration can be achieved in 10 different ways as shown over here. So these are different ways. This is another way of depicting the same thing, instantaneous configuration. Here the particles have been shown as a rectangular block, as blocks, as rectangular blocks shown over here with different colors. And so the same 10 pictures, you can see 1, 2, 3, 4, 5 and 10. So these are 10 different configurations that can be achieved for 3, 2, 0. 3, 2, 0 configuration. Okay, so this is how you simply you can work out these details if you try starting with this. So similarly, if I ask you to find out in case of if you have total 8 molecules and you have to achieve a configuration where you have 6 in the 6, 2, then what will be the number of configurations that you can find out. You can do this exercise. I am leaving this as an exercise for you. So so the statistical weight of a configuration, we are now trying to find out how we have got to this expression, the expression that we talked about, this expression. We are going to discuss this in detail, how we arrived at this expression. That is, we are going to derive this equation. Coming back to it, that is statistical weight of this. So that is, we are going to find out how this weight of a configuration can be found. Expression for the weight of a configuration can be found. So the first ball, if you have n number of molecules or n number of particles, the first particle can be placed in n different ways. Then the next ball will be will be having n minus 1 different ways for placing the remaining, and so on. So therefore there are n into n minus 1 into, and so on, you go on decrease n minus 2 and so on up to 1, which will be equal to n factorial ways of selecting the balls, selecting the particles for distribution over the different baskets. First consider the weight of the configuration, this n minus 2, 2, 2 and 0, 0, 1. So there are 2 particles to be promoted to the first excited energy level. The first particle that you select has n number of ways. The second particle that you will select will have n minus 1 number of ways of selection. So you combine these two choices, n into n minus 1, these are your total choices. And because for every particle that you select, so each one of them you have 2 ways of doing it. So actually you will achieve 20. If you are considering this way, then you should have there should be, at least if you are considering the last one, in which we had a total of 5 molecules, out of which 2 were to be placed in the higher energy, we should be achieving, simple consideration of the choices will give you n into n minus 1. But we should also note that if we have particle A selected, particle B, AB configuration and BA configuration are the same, so that we will have to divide it by half. So when we divide it by half, the n into n minus 1 by 2, this factor has to come into picture, and we get the total number of ways will be for getting a distinct configuration, distinguishable from each other, that will be half into n minus 1. Okay. So now, so this remark can be generalized for any instead of 2 energy levels, we can infinite number of energy, we can have infinite number of energy levels, or we can say that we have infinite number of baskets in which we want to place this n number of particles. So this is just a view, 3, 4. If you suppose you have 4 energy levels are there and you have 18 molecules to place, then how many different ways you can have. So just take a look over here. We have if n is equal to 18, and there is this is, so you have, and this is the first energy level, that's first basket. You can, if you fix that in the first basket, that is epsilon naught, you can place only 3 atoms. The second basket can have only 6 particles. The fourth basket will have only 5 particles. The sixth and the third basket will have 5 particles, and fourth one will have only 4 particles. Then how many different ways you can have of achieving this configuration? So if you apply this, then you will find that the 18 molecules shown here can be distributed into 4 baskets, and in 18 factorial ways. Now we are also trying to fix that each of these baskets can have accommodate only certain number of balls or particles that we are considering. So if there are 3 factorial ways of selection that put 3 molecules in the first basket, and there are 6 factorial ways in which 6 molecules can be selected and put into the second basket, that is second energy level, epsilon 1 energy level, and so on. So the distinguishable arrangement would be like 18 factorial divided by 3 factorial, 6 factorial, 5 factorial, and 4 factorial, like this. So similarly, if there are n1 number of ways in which n1 balls can be placed in epsilon 1, if we choose epsilon 1 as our basket, so epsilon 1 is your basket, n1 is the number of balls that can be selected in this, and total number of balls is n, given by capital N. So the number of ways you can do it is n1 factorial. Similarly, if you have, this is there are n2 number of particles that can be put in this second basket, which is labeled as epsilon 2, the corresponding to the energy level. So in that case, you will have the number n2 factorial with the number of ways you can do that, and similarly, and so on. So in total, if you regardless of the order in which the balls are chosen, we will have n factorial divided by n naught by n1 factorial, and so on. This was the equation that we had derived earlier, and that we were showing the expression earlier. So this is the thing. So this is how we, by a logical sequence of discussion points, sequence of points, we can put through our points in a sequential manner, and we can arrive at this kind of description, that total number of ways for n number of molecules to be put into epsilon 1, epsilon 2, epsilon 3 energy levels would be n0, n1, n2 factorial. And so when we have a limitation of how many molecules can be adjusted in one energy level. Okay. So some example is illustrated over here. So you calculate the weight of a configuration in which 20 objects are distributed in the arrangement 1, 0, 3, 5, 10, 1. So simply it's now you know the formula, you have know the expression, how to find the number of ways, different ways. So this number of ways that you can do achieve this kind of arrangement is your statistical weight W. So in this particular case, 20 factorial divided by 1, 0, 3, 5, 10, 1 factorials. So this gives you, these are the different ways you can do that. So it will be, so it becomes even easier if we consider, instead of taking W as a whole, as such a large number, it was coming out with 10 to the power 18 or something. If you take log of W, a natural log of W, that becomes even easier to, so the expression becomes even easier to understand. So we can have ln W, which is equal to take the log of the whole thing. So if you take this log of this, it will be ln n factorial and minus ln n naught factorial, n1 factorial, n2 factorial, and this whole in the bracket. So further solving this equation, you can write it in this way, that the summation ln factorial, this whole thing is summation of ln ni factorial. So it reduces to this. So the entire description is reduced to this form, that is ln n factorial summation ln over I ln ni factorial. So so we have used the equation. So basic mathematics is being described here. So for those who are with a non-maths background, they can pay attention to that. I think it is much easier to do. How so if you simple expression how a log x by y can be expanded, that is given over here. So by introducing ln w, it is easier to make approximations. In particular, we will be using Stirling approximation form, that is ln x factorial is almost equal to approximately equal to x ln x minus x. So this expression will be helping us in simplifying the mathematics. So the expression for the weight is, if we employ this expression of Stirling approximation, then you can substitute that for in the expression of an nln. So we had n factorial, so you n ln n, you write that minus n, and similarly ni factorial was here, summation of ni factorial, so again you write ni ln ni minus ni factorial. So if you sum it over, if ni is summed over the value of I variable, this will be equal to n, right? So minus becomes plus, and this term will cancel out, these two terms will cancel out, and you will be left with nln minus summation of ni ln ni. Okay, so so configuration is n minus 2 2 0 dominates over this is what we have already discussed. The number of ways of having this configuration is more than this, and there is more likelihood this kind of expression, there is more likelihood of achieving this configuration than this. And it should be easy to believe that there may be other configurations that have much greater weight than both. It is we will see that, in fact. So there will be some configuration which will be so great in weight, statistical will be so high, that will be most dominating than the others. So in all the system, this kind of thing will be found when we discuss individual cases of a system. So the properties of the system will therefore be characteristic of that particular dominating configuration. If we have such configuration which is more dominating than the others, then the properties that we will be averaging will be a representation of that particular configuration which is more dominating. So because w is a function of ni, we can do this search by varying the ni and looking for the values that correspond to dw is 0. So most dominating configuration, if you have plot w versus n, then if you dw by dn, if you perform, you can find the maximum of that derivative will give you the point where if you plot first derivative, you can find out where dw is getting 0. And so you have already applied the first derivative method in some practical classes in the lab, so you are aware of this fact, how to find the maximum of a function by performing this. However, there are two difficulties in this procedure. First difficulty, that only one permitted configuration. So now we are slowly moving to the part of so far that while discussing different populations, we ignored this part, that the total energy has to be kept constant. Now we are going to introduce this part, and obtain the expression in a more in a manner that will be realistic. First difficulty is the difficulties, two difficulties that we are pointing out in the above procedure is that uh, only permitted configuration are those corresponding to specified constant total energy of the system. This requirement rules out many configurations, such as in the previous case we have been discussing one in the first configuration. This is the second configuration. But if we do it in this way, then the energy of the two systems are going to be different. So both cannot. So the total energy of system cannot be kept constant if we have this kind of thing. So it can be possible these two configurations if epsilon and epsilon were degenerate. Only in that case these two configurations are possible. Otherwise not. So. So in looking for the configuration with greatest weight, we must ensure that configuration also satisfies this condition. That is, total energy has to be constant. And so now we can write total constants for taking this into consideration, that Ni, the number of molecules into epsilon I so number of molecules in energy level epsilon I is, so the total energies of the summation of this n into E, n into epsilon should be equal to capital E, as shown over here. This is the total energy of the system. Total energy of the system, and this is the summation of all the energy that each of the particles possess as per the population. So the second difficulty is that because the total number of molecules present is also fixed, n is fixed, we cannot arbitrarily vary all the population simultaneously. Thus, increasing the population of one state by one, when you increase the population of an energy level, it also means that there must be a decrease in the population of another state. So this is the consideration that will also come into picture. So when you search for maximum value W, we always these are subjected to this condition. Mathematically, you can write it in this way, that total number of molecules capital N has to be constant. So summation of Ni must be equal to N. Summation of Ni, constant total number of molecules. So these are two conditions that we have now incorporated in our previous description of the number of ways, the statistical weight. Then it can be shown that the population in the configuration of greatest weight subject to the two constraints in the above mentioned equations, and it will depend on the energy of the state according to the Boltzmann distribution, which is given by this. Ni is the number of molecules in energy level epsilon I, and this is the total number of molecules. So summation of these two we can take, so this can be shown by, so this is the expression of the Boltzmann distribution, epsilon I, so Ni is given by this, and total N will have this expression. So so beta here is the parameter that will distinguish, that is a very important parameter, and this is basically 1 by kT in such cases. So this determines the most probable population of the state of the system. So most probable population of the states of a system can be given by this expression, and this gives you the relative ratio of the populations, and beta is here the 1 by kT term, and T is the thermodynamic temperature, and we call it Boltzmann constant. So temperature is the unique parameter that governs the most probable population of state of a system at thermal equilibrium. So we can see that it is the temperature only which is able to distinguish between different states which are in thermal equilibrium for a system that is in thermal So so relative population of states, the sum of the denominator of Boltzmann distribution need not be evaluated. We don't have to, when we are talking about, that was for the, when we are discussing Ni by Nj, so that there is energy, you have energy level 1, energy level 2, epsilon 1, epsilon 2, and if you want to calculate the relative populations, then you have to have number of molecules in the energy level 1 by number of molecules energy level 2. You can calculate using this. So you can see that the expression that we had earlier, that capital N, that summation factor is gone. Summation. So if you for relative populations, we can easily find out of the two energy levels if you can by this expression. So beta epsilon e to the power minus beta epsilon ei by e to the power minus beta epsilon j, and so simply put it, you can write it in this manner: e epsilon I minus epsilon j in the bracket along with beta as an exponential term as a. So this simple expression is very important for understanding the range of all the ranges of chemical phenomena that we study in vibration, molecular vibration, rotation, everything. So the relative population of two states falls off exponentially with their difference in energy. This is an important message that is hidden and that is conveyed by this expression, that it is a minus sign and there is decrease. So as you move from lower to higher energy side, there will be fall in the population, and that fall will be exponential as represented by this equation. So relative population of two states falls off, that it decreases exponentially with the as the difference in energy is larger, there will be greater fall will be expected. So the Boltzmann distribution contains a much richer variety of information than the relative population of states. We can so now we can we introduce a new concept here that is called partition function. So it is related to the Boltzmann distribution, as we have seen the expression e to the power minus b I epsilon I that we have earlier derived, earlier stated, and pi here is the fraction of molecule in the state I, that is denoted, pi is given by Ni by n, and q is the molecular partition function. This molecular partition function is denoted as epsilon e, summation of epsilon, e to the power minus beta epsilon ei. So we are correlating over here. You can see that summation that we are taking of this term over different energy states. So that has been hidden here. The q has been expressed as epsilon, summation of epsilon taken as for the decaying function, which is represented by this term minus beta epsilon naught. This is the exponential term over here, which is the same. You can see this is we are getting this from the Boltzmann expression for population that has been written in a different way, and the summation part is this is now our denominator. So Ni by n is pi is Ni by, a different way of writing Ni by n is this, and this the denominator now we are terming it as molecular partition function. So it may happen that several states have the same energy, that is, we say that they are degenerate. There may be cases some energy levels have more than 3 or different ways of orientation, and then you say that they have same energy, same energy state with different orientations, that we say that degenerate systems. So they will have same contribution to this sum. If for example, Gi is the states, Gi is the states that have the same energy, that is Gi. We can say that Gi is the degeneracy of the system of the energy state epsilon I. Then we say that it is Gi fold degenerate, and we can write the expression as Q. The molecular partition function then can be written as Gi, the degeneracy factor, and then the exponential term as we have earlier. So the sum is now over energy levels, sets of states with same energy. Okay, so now we can discuss some examples over here, how to write partition function. For example, if you are asked to write a partition function of HCl molecule considering it as a rigid rotor, so we will be using the equation that we have discussed in previous slides. We also need to know the energy levels, energies of the levels, and also the degeneracy. These two things you must know before solving the problem. And so rigid rotor constant that you have already studied in quantum mechanics, that will be helpful here. So partition function, we express the energy of the levels relative to 0 for the state of lowest energy. So energy levels of a linear rotor can be given by HC, B, J. Actually, it should be B bar if we are expressing in CM inverse. J into J plus 1, with J is equal to, J is the quantum number, rotational quantum number, 0 expressed as 0, 1, 2 and so on. The state of lowest energy has 0 energy in this case. When you put J is equal to 0, this whole term will be 0. So we don't need any adjustment. Remember, we will be needing, will require adjustment when we deal with vibrational energy, because there will be, even at when the vibrational quantum number is 0, you have certain energy left with the system. So we have this degeneracy 2j plus 1. So we can now write this expression as Gi as 2j plus 1 degeneracy, and the expression of the epsilon j, the energy of the rotational energy levels, is Hc Bj j plus 1. And so this is the expression of the partition function, which can be written for HCl molecule. If you have been provided with the values of B and J, you can evaluate this thing easily over a different temperature. So however, it must be emphasized that this expression is only valid for unsymmetrical linear molecules such as HCl, and not for CO2. So we can obtain some more insight into the significance of partition function by considering how Q depends on temperature. Now consider when T is close to 0. When T is 0, what will happen to this term, beta term, 1 by kT? It will become infinite. Then every term except 1 in the sum defining Q is 0, because so the expression that we have we have shown in the previous slide, you can think the exponential term which is in which the Q will become 0 in the denominator, because each one has the form e to the power minus x with x to the power infinity. The exception will be where you have epsilon naught is equal to 0, or the G naught terms at 0 energy, if the ground state is G naught for degenerate. In that case, E naught by kT will be equal to 0, whatever be the temperature, including 0. So this E by kT, we are getting beta multiplied by E naught term, if it is there as the exponential term. In that case, if E naught is 0, will be this whole term will go to 0. Beta epsilon term will be 0 at all the temperatures. So we are if now consider another case when T is equal to 0. In that case, so now we are reaching a simplification. We are trying to find out in the limit when temperature tends to 0, what will be the molecular partition function. So we find that the exponential term is reduced to 1, and we are left with, because E naught by kT term goes to 0 in this case, so we are left with, and when T will be 0, you are lowering the temperature, all the molecules will be in the ground state. epsilon 0, and the epsilon 0 so the E naught by kt term becomes 0, so the exponential term becomes 1, and the q will be equal to g naught. So this is the term expression. You have to simply substitute the values given the expression for in the given expression for q, that is the partition function. So the exponential term will become 1 because all the terms E naught by kt is equal to 0, and so in the limit if you state it in words, you can say that at t is equal to 0 the partition function is equal to the degeneracy of the ground state. Now let us consider the case when T is so high, that is we are raising the temperature and making so high that each term in the sum Ej by Kt is now equal to 0. So if temperature is too high, that is it reaches infinity, then also this term will go to 0. If you are approaching infinity, T is going to be is effectively, if this term goes to it becomes approximately 0, then again e to the power minus x term will be 1 when x is 0, and this contributes 1 to the whole expression of partition function. It follows that sum is equal to the number of molecular states, which in general is infinite. So in that, so the expression when T is approaches infinity, temperature approaches infinity, the Q will become infinite. Sum of the number of, so we are the only, it is, so that is what we can say, that all the, when you reach infinite temperature, all the energy levels, all the possible energy levels will be equally populated. All of them will be having equal populations. So the possibility of such energy levels will be infinite. You have quantum number n is equal to infinity, v is equal to infinity is possible. So it will be, the number of ways that you can put it is also infinite now. So in some idealized cases, the molecule may have only a finite number of states, then the upper limit of Q is equal to the number of states. So in general, number of energy levels can be infinite. We have seen that in quantum mechanics, that we discuss cases where up to n is equal to infinity. In case of electronic transitions, we have discussed. So in other cases also, in vibrational motion, rotational motion, we have the quantum number can increase as an integral as an integer up to infinity. So at infinite temperature, it is possible you will have all the states become accessible, and you have this partition function becomes infinite. The molecule may have only a finite number of states, then the upper limit of Q is equal to the number of states. So, this case is applicable in case of spins, because in spin we can have only quantum, the magnetic quantum number, spin quantum number, M.Sc can have only 2 values, and in that case the total possible number of partition function is limited by that number. If we consider only the spin energy levels of a radical in a magnetic field, then there would be only 2 states as given by this ms plus minus half. Partition function for such a system can therefore be expected to be rising towards 2. The maximum value that we can have will be 2 as t is increased towards infinity. So now we try to understand what are the significant points, what is the significance of this partition function basically. So the molecular partition function gives us an indication of the number of states that are thermally accessible. So there may be, as we describe a molecule, even in hydrogen atom, we say that there are n is equal to infinity is possible, but not those all the states energy levels are possible. Is accessible at room temperature. That is, if you provide certain temperature, gradually energy will increase, and then the system can the particle can molecule can have can move to the higher energy levels. So this is what we mean accessibility of energy levels. So all the energy states, this number of states will not be accessible at all the temperature. If you have at T is equal to 0, you have one scenario which is at T is equal to 0, only the ground state is accessible. All the molecules will have same energy, epsilon 0 at T is equal to 0. And as you gradually increase the temperature, epsilon 1 becomes accessible at certain temperature. Then if you some molecule move to epsilon 1 state, then if you increase the temperature further, epsilon 2, some molecules may move to epsilon 2 energy state, and so on. And at the other extreme, you increase the temperature to such a high value that all the energy states are accessible equally. So the population in all these energy states will become equal. So at T is equal to 0, only the ground state is accessible, and Q is equal to G naught. At very high temperature, virtually all states are accessible, and Q is very large value. And when T is infinite, you can say this Q becomes infinite. So we also apply the concept for to calculate the partition function for a harmonic oscillator. So you have already in quantum mechanics classes, you have already learned how the spacing between energy levels in a harmonic oscillator is. How does it vary? There is equal spacing in the harmonic oscillator, as we know, which can be denoted. Here we denote the lowest energy level as 0. We have stated this principle in the statistical thermodynamics. We always take the lowest energy level as 0. And later on, we make adjustments if it is required, considering the fact that the lowest attainable energy state is not actual energy is not 0 in that case. So we will do it in that later. But so first thing is that we have this is the spacing of energy levels in a harmonic oscillator, and we also now know that each of these energy states are non-degenerate. There is no degeneracy in a harmonic oscillator. So we expect that the partition function will increase from 1 at T is equal to when T is equal to 0, the partition function is equal to the degeneracy, and degeneracy is 1. Okay, there is only one possibility of T is equal to 0, it is equal to 1, and as we approach infinity, when the highest quantum number that is equal to infinity is achievable, at T is equal to infinity, the whole function goes to infinity, becomes infinite. So taking the separation of energy levels to epsilon is equal to h mu, so the individual levels lie at the 0, epsilon, 2 epsilon relative to the ground state. So we need to evaluate the partition function as denoted by this levels. Each of the energy levels, I is 0, I is equal to 1, 2, 3, and so on. This is the degeneracy. GI term will vanish because it is equal to 1, so we don't have to worry about this. We have to only evaluate this summation of this term, exponential term. So summation of this term, energy levels have to be done in this manner. We can make use of this mathematical relation to simplify the equation. 1 plus x square e to the x square is can be expressed as 1 by 1 minus x. So if we have exponential term, 1 plus e to the power x square and so on, like that, we can make it. The sum of the infinite series S1 plus x square x cube is obtained by multiplying both sides by x. So if you multiply with x to this term, so this becomes x plus x square x cube plus x, which is, you can also write it as s minus 1, and hence s is equal to, capital S is equal to 1 by 1 minus x. The partition function then becomes, you can write this expression, q is equal to this 1 plus e beta e q e. Apply this relation over here. So this is your 1 plus x, x square, x cube, and so on. So 1 plus x, x square, x cube, and so on. So then this becomes 1 by 1 minus epsilon to the power beta e, 1 by 1 minus x. So this expression, if you plot it against kt, this is the partition function, epsilon is equal to 1 by kt. So kt, if you plot it at kt by epsilon, this will look like this, wherein the function has been plotted. So this is how you will get the curve, right? So this is the expression this is how the graph will look like if you plot this partition function as a function of kt. So this is, so q rises from 1 to infinity as the temperature is increased. We can conclude that the fraction of molecules in the state with energy epsilon is, you can so P population, the way we describe it now, Pi is the energy of e to the power minus beta epsilon I by q, and then we put it over here, substitute these values, simplify it, you substitute the value of q, and the expression would be like this. So this is your expression for the population variation with temperature in simple harmonic oscillator, can be shown, can be discussed using this expression, okay, that we have for the partition function. So this is what the picture would be looking like. So when you have at lower temperature, you have only almost all the molecules are having in the ground state with some at lower temperature, not zero but low temperature, you have this kind of situation. And then when you increase the temperature slightly, you have increase in the molecular partition function, and the distribution changes like this. Then further increase in temperature, the higher energy states are also becoming accessible now, and at a very high temperature you have a good the same total number of molecules, keeping the total number of molecules same. This is the distribution will look like. Okay, so remember, the lower energy levels will always have a higher population. Unless you go to infinity, temperature infinity, then all this will be equal. This you should understand how this drawing has been made. So this bar at the bottom that you show, this is showing the population. So there is and some of the molecules are over here, and this total length of the bar will be distributed all along these energy levels as the temperature is increased, and so this bar is reduced and some of this is being promoted over here. So that represents that some of the molecules have been promoted over to this energy level, to this energy level, and so this length of the bar shows the population of this state, and the total length of the bar we have to keep the same as we will obtain from by combination of this plus this. That is, total number of molecules have to be equal in all the cases. So the distribution will look like this, and finally you can imagine a stage will come when temperature is very high, reaches infinity. This will all look equal. The population of each of the states will become equal. So at very low temperatures, Q is close to 1, only the lowest state is significantly populated. As the temperature is raised, the population breaks out of the lowest state and the upper state become progressively highly populated. So we say that higher energy states are now becoming accessible as the temperature is gradually increased. At the same time, the partition function rises from 1, this is a partition function is initially 1 to 1.58, 1.99, 3.86, you can see. Indication range of states populated. the partition, so the name partition function, now you can understand this is what we mean by saying why it has been named as partition function. It is the sense in which Q measures uh, how the total number of molecules is distributed. That is over. So there are certain available energy states available, and the molecules have been distributed amongst those energy levels. Or we can say that we had a certain number of available energy states, and we are partitioning the molecules into them. So that's why we can say that the molecules have been partitioned over different sets of available energy states. So this is how it shows that kind of how the partition is being done. That's why we call it as partition function. How this partition of molecules with respect to the energy levels is being done. That part is shown by this function, and that's why we say it as we label it as partition function. So that's all for today's class. I hope we'll continue with this in one more class. I would like to finish. So that's all for today. Goodbye.